Up next, we have Praveen. He also attended MTTS Level 1 this year in ISA Pune. He's going to talk about Banach Contraction Principle, and he's a student in ISA Trivandrum currently pursuing integrated MSc PhD.
So before starting, I would like to thank all the audience who are present here, and I would like a interactive seminar. Okay, so yeah, I'll start. Hello everyone. So let's discuss about Banach contraction principle. So for this, let's first discuss what a contraction actually means. This word contraction is a very familiar word to us, right? And we are using that in our daily life, isn't it? And we do have an intuitive picture of what it is. So I would like to begin with a question. What do you feel as a contraction? Or when we say contraction, what comes to your mind? I would like a answer from your side. Yes, Vaishnavi.
We say contraction as like shrinking, something like that.
Okay, shrinking. So suppose a object shrinks. Okay, as we say, as it contracts, what happens to the points on that body?
Decreases.
Yeah, so they come closer, right? So the distance between them decreases. I hope that you meant that. Okay. Yeah. Thank you, Vaishnavi. So,
Thank you.
as Vaishnavi said, when a body contracts, the distance between the points decreases. And intuitively, when we say, okay, suppose we are considering a square in front of us, and suppose that it is shrinking, okay, then essentially, what do we mean? Uh, can it shrink in any way, or is there anything more to that? Just have a think just think about that. And essentially when we say it is shrinking, we are saying that there is a kind of uniformity in that kind of shrinking, right? So suppose that square, the you are cutting it in half, the left half shrinks to half of its size and the right hand side shrinks to 3 by 4th of its size. This now we actually don't have a square in front of us, right? So and this does not go well with what we have in our mind. Okay, so the distance between the points decreases, and of course there is a uniformity, and mathematically we say that the distance between any two points reduce by the same factor. Okay, so this is what we have generally in our mind when we say contraction. Now mathematically we want to define contraction precisely. Okay, so how can we make it more rigorous? So let's think about it. First we have a set, okay, call it capital X. On that we have points, say X and Y, and then contraction happens, and then we have something like X dash and Y dash. Now the distance between X dash and Y dash is strictly less than distance between X and Y. Okay, now this is true for all the pair of points X comma Y. Moreover, when we are shrinking, as we said, there is a common factor by which the distance decreases. So essentially, if we have X and Y in the one set X, after contraction, we have distance of X dash comma Y dash is less than some C times distance of X comma Y, where C lies between 0 and 1. Okay, so essentially we can see that, okay, X goes to X dash, Y goes to Y dash. So it's a kind of mapping, right? So and what are we mapping from? We are mapping from a set on which we can talk about distances, right, to another set on which we can again talk about distances. So essentially we are actually considering a map from one metric space to another metric space. Okay, and what is the speciality of that mapping? The speciality of that mapping is that if we are taking 2 points X and X dash in the domain, okay, its image will be T of X and T of X dash, and the distance between T of X and T of X dash is less than or equal to some constant C times D of X comma X dash for all X and X dash in the domain. Okay, so this is how we would like to define contraction. Now what do we have in front of us? We have a map. We would like to study this map. Right, now when we say we want to study a map, we essentially mean that we want to study the properties of map. So what are some desirable properties that we would like to have? The question is to audience. We have a map here from one metric space to another. what is a desirable property? Yes, Shyama.
Continuity.
Continuity. So if we have continuity, then we have many results with us, right? So continuity is a very desirable feature. And what do you think, Shyama? Do you think this map is continuous? What?
I think it's continuous.
Yeah, okay, thank you, Shyama. So intuitively, when we feel okay, something is there and it is contracting, so we feel it is a continuous map, right? This contraction is a continuous map. Okay. So of course, if we believe that it is a continuous map, we would like to write down the epsilon delta definition for that. And I urge the readers to, the audience to write down the epsilon delta definition. Now, before that, I would just like to make one observation, an interesting observation. That is, here we have a map, and the distance between the images, this t of x and t of x dash, is less than or equal to some constant into distance between the points in the domain. Right? Now, this feature, this is a very familiar feature to us, right? This characteristic. This is something that we know as Lipschitz condition, right? So here we have a map that satisfies the Lipschitz continuity. And we know that any function which satisfies the Lipschitz continuity will definitely be uniformly continuous, right? So actually we were demanding very simple thing. Okay, we were just trying to study if the map T is continuous. Okay, and we believe that it is continuous. So we tried to write down epsilon delta definition. That is one thing. Now, other than that, we just looked at the definition of the contraction. Okay, in that we see that by definition we have distance between the image points is less than or equal to distance between the points in the domain. So we say that this map T satisfies the Lipschitz criterion. And we know that in metric space, if a function satisfies the Lipschitz continuity, it is uniformly continuous, which is a more powerful statement, right? So the function T, the map T is uniformly continuous, and hence it is continuous. Okay, so we have a very good map in front of us. Now, okay, the results regarding continuity and all will follow from this. Now, we would like to see how this map T acts on some metric spaces. Okay, that means let's study some examples. Okay, for that we will take a very simple example. Our favorite metric space. We will take some closed bounded interval in R. Here, for example, I am taking a map T from closed interval -2 to 2 to itself. Okay, and here the T of x, I am defining it to be x by 2. Okay, clearly it is a contraction map, right? I will also show you the graph. Okay, so here we have the domain with us. Okay, and then here we have the image. So the closed interval -2 to 2 is actually getting mapped to closed interval -1 to 1. Okay, from this graph or from this image, can you observe anything? Yes, Devika?
Here, 0 is a fixed point.
Yeah, 0 is getting mapped to itself. So 0 is a fixed point. Okay, now is there any other point that is fixed?
No.
Okay, so you are saying that there is no other point that is fixed. Can you just try to prove it?
Okay. A point x is said to be fixed if t of x equal to x. That
Right.
is x equal to x by 2. X minus x by 2 has to be 0, which implies x by 2 is 0, which implies x is 0.
Yeah, thank you, Devika. So here we are observing two things. As Devika pointed out, we have that 0 is getting mapped to itself. That is, 0 is a fixed point, and 0 is the only fixed point. Okay, so here the fixed point is unique. Now, I also would like to add one more thing. Suppose we are starting with 2. Okay, so 2 is getting mapped to 1. Okay, so T of 2 is 1. Now, after that, suppose we are considering the 1 in the domain, that is again getting mapped to 1 by 2. So actually T of 2 is 1, then T of 2, okay, which is equal to T of 1 is 1 by 2. Okay, if I am applying again T of 2, we will get map T of 1 by 2, which is 1 by 4. So here we are actually starting with 2 and we are actually moving closer and closer to 0, right? Similarly, start with -2. it is getting mapped to -1. Now apply the map t on this -1. So we'll have t of -1 is -1/2. Then apply this t on -1/2. So we'll get -1/4. Again, even when we are starting with -2, we are moving closer and closer towards 0. Okay, so you can observe this for any point. Okay, so start with any point. One second. Yeah. So for any x in -2 to 2, we will have this. If we are keeping on applying t to that point, if that is if we are applying t power n on that x, if n tends to as n tends to infinity, this will get closer and closer to 0. Okay, so these observations, this we are trying to generalize. Okay, so there are mainly three observations. One is there is a fixed point. Second one is the fixed point is unique. Okay, and third one is start with any point in the domain. Okay, now keep on applying the contraction map on it. Okay, that is apply t power n on x, and as n tends to infinity, this will this sequence, if we are taking it as a sequence, it will converge to the fixed point. Okay, so these observations, it is actually true for any complete space, and that is exactly Banach contraction principle. Okay, so here observe that -2, 2 was a closed and it is a complete metric space. Okay, first we'll observe that it is a complete metric space. Okay, so the Banach contraction theorem says that if you start with any complete metric space and if you have a contraction on it, then that map T will have a unique fixed point. Okay, that is, it has a point T such that T of x is equal to x. Moreover, if we are having a sequence xn, which is obtained by repeatedly applying the map T on it, eventually that sequence xn will converge to the fixed point. Okay, so we actually observed it in the one case, and we are generalizing this. And this general theorem, I'm actually not going to prove it, and I would ask the audience to prove it afterwards, because the proof is more or less direct computation. I'll just give the proof outline. Okay, and in the statement of contraction principle, we also have a bound of to find how the sequence is behaving. Okay, so let me quickly give you the outline of how to prove this. Here we'll begin with the sequence xn. Okay, and we know that this sequences, it is as the distances are getting closer and distances are becoming smaller and smaller, the points xn will get closer and closer. That means we'll have the sequence xn to be a Cauchy sequence. Okay, and we have a Cauchy sequence in a complete metric space. Hence we know that the sequence xn will converge. Call that limit as x. Okay, we want to prove that t of x is actually equal to x. That is x, that limit is the fixed point. That will actually follow from the continuity of t. Okay, we know that t is contraction, and we already proved that t is uniformly continuous and it is continuous. Okay, so from the continuity of t, we will get that x is a fixed point. Okay, so that is the proof outline, and the uniqueness also follows from that similar computation. Okay, now I am skipping the proof so that I can discuss more about the importance of various assumptions in the hypothesis. Okay, in the hypothesis, observe that we are saying that we need it to be a complete metric space. Okay, we also want T to be a contraction. We'll check what will happen if we are removing one of the hypotheses. Okay, so first, what will happen if x comma d is not complete? Okay, just think about this, and suppose the x comma d we are beginning with is not complete. Will the conclusions be true? I'll give you a hint. Just think about the example we begin with. We talked about -2 to 2, right? So try to make it a metric space which is not complete. Okay, and show that what happens. Okay, the question is to audience. Do you have any answer? Someone has raised hand. Yes, Shama.
Can we take x equal to -2 comma 0 union 0 comma 2 and define the map t from x to x such that t of x equal to x by 2?
Okay, so here Shyama is taking the same map, and then from the closed interval -2 2, she's simply removing the point 0, right? Okay, yeah. So here definitely this metric space x is not a complete metric space. That we all agree, right? Or take a sequence 1 by n in X, okay, where n is a natural number. Definitely that is a Cauchy sequence, and it will not converge, because if at all it converges, it has to go to 0, and here 0 is not there. Okay, so that sequence does not converge. Hence here X is definitely not a complete metric space, and here we also don't have a fixed point, right? So we cannot remove the completeness from the hypothesis. Okay, so in the hypothesis of Banach contraction principle, the X comma D, the metric space being complete, is very important. Okay, now suppose T is not a contraction. Okay, we had two hypotheses, right? One is X is complete, the other one is T is not T is a contraction. Now suppose T is not a contraction. Okay, that means here the C, the factor C, is not less than 1. Okay, so suppose that C is equal to 1, or that's the simplest case we can think about, right? So what will happen? Will the results hold true? What do you think? Yes, Nandana? Okay, I think there is some net issues. Okay, so do anyone else have an answer? Okay. Okay, now suppose this is not a contraction. Okay, let's think about a very simple case. Okay, consider a map from R to R. Okay, just consider the translation. Okay, so that translation will leave no fixed points, right? Suppose I am translating by 1, so X will go to X plus 1. Okay, so that I am defining T of X to be Cx plus 1, where C is equal to 1. Okay, so we will have T of X is equal to X plus 1. Okay, will this map have any fixed point? Suppose it has, then what will happen? We will have X is equal to X plus 1, right? That means 0 is equal to 1, which is absurd, right? So in this case, it will not be, we will not have any fixed point, right? So in the hypothesis of Banach contraction principle, T being a contraction, that means there being a C such that 0 is strictly less than C, and C is strictly less than 1. This is very important. Okay, so T being a contraction is of utmost importance. Okay, so now we have discussed about the motivation for Banach contraction principle, and also the importance of the hypothesis. Now suppose we are starting with some other hypothesis. That means here, as I said, we are actually starting with a contraction, and in that contraction we have distance of T of X comma T of Y is less than or equal to some constant C times distance between X comma Y. Now suppose I am assuming a weaker condition. Okay, that means distance between T of X and T of Y is just simply less than distance between X comma Y. Okay, note that this is different from the earlier case. Okay, in the earlier case we had allowed C is equal to 1, and so distance between T of X and T of Y will be equal to distance between X comma Y. Here we are assuming a better condition, but this better condition is not as strong as the contraction. Okay, so I am assuming that distance between T of X comma T of Y is strictly less than distance between X comma Y. Is this sufficient? Okay, to get the same results as what we had in Banach contraction principle, is this sufficient? Okay, that is the our interest, next point of interest. Okay, so now the result, of course we obviously feel that the result is not true, we do not have the conclusions. That's what we essentially feel, and of course that's a correct intuition that we are having. And the example is not very trivial, so let me directly give that. So consider X is equal to closed 1 to infinity, and the map here I am taking is T from X to X, defined as T of X is equal to X plus 1 by X. Okay, now here we are having a function which is defined on a subset of R to R, so it's actually a real function, right? Now from using this, my claim is that distance between T of X comma T of Y will be less than distance between X comma Y, but will not have fixed points. That is my claim. Okay, I am giving you this claim. Can you think of how to prove this? Okay, let me observe some more things. Here T of X is actually differentiable, okay, on 1 to infinity. And because we are having a very nice function here, X plus 1 by X, and here we have t dash of x is actually equal to 1 minus 1 by x square. This much things we can observe. Yes, Gopika?
We can use mean value theorem.
Okay, so what does mean value theorem tell us?
Here t is continuous and differentiable. So there exists an element z between a and the endpoint such that t of x minus t of y by x minus y is equal to t dash of c.
Okay, yeah, thank you, Gopika. That's exactly what we were going to do. Okay, so essentially she has given the proof as well. So we will use the mean value theorem. Okay, and that we'll have t of x minus t of y divided by x minus y is equal to t dash of some xi. Okay, which lies between x and y. Okay, we will take the modulus on both sides. Okay, and what do we have? Here we have t dash of x is actually 1 minus 1 by x square. Okay, so what will be t dash of xi? It will be 1 minus 1 by xi square. Okay, but where does xi lie? Xi lies between x and y. But where does x and y lie? It is in 1 to infinity. Okay, so xi is also in 1 to infinity. Okay, so this 1 minus 1 by xi square, this 1 by xi square is definitely positive, and 1 minus 1 by xi square will definitely be strictly less than 1. Okay, so here we'll have t of x minus t of y is equal to t dash of xi into modulus of x minus y, and since t dash of xi is strictly less than 1, we have distance of t of x comma t of y is strictly less than distance between x comma y. Okay, so this part, this hypothesis is definitely being satisfied. Okay, now let's come back to the function t of x. Here t of x is equal to x plus 1 by x. So here again this 1 by x is definitely a positive quantity, right? So we will have t of x is equal to x plus some positive quantity, right? So it will never be equal to x, isn't it? It is, since t of x is equal to x plus 1 by x, here we will have t of x will be strictly greater than x. So t of x can never be equal to x. Hence, there will be never be a fixed point. Okay, so let me just summarize about this example. So we were trying to see, we saw that if c is equal to 1, then definitely we can use translation, and we saw that the results or the conclusions that we get in Banach contraction principle does not hold. Now we were trying for something else. We were trying to look for a easier or simpler condition. Okay, so we were looking. Suppose we are starting with a map which is not a contraction but satisfies this condition. Okay, distance between t of x comma t of y is less than distance between x comma y. We were checking, is this sufficient to get the same conclusions as Banach contraction principle? The answer is no, and the counterexample is t of x is equal to x plus 1 by x. Okay, so this map satisfies this condition, but it does not have any fixed points. So we will not get the same result as Banach contraction principle. Okay.
So what if we are beginning with a compact set? What if X is compact? Will the conclusions similar to Banach contraction principle hold or not? The answer is yes. Now, why is that true? Or what is the crux, or what is the thing that caused a big change? The thing is compactness. Okay, so I'll just be outlining the proof, and here the main crux of the proof is that if we are considering a continuous function on a compact set, it will attain its maximum and minimum on that compact set. Okay, so consider a function phi defined from x to r as phi of x is equal to distance between x comma t of x. Now this function phi is continuous on the compact set, and hence it will attain its minimum. Okay, now let it attain its minimum or at the point x naught. Okay, now we know that distance, by definition of distance, we'll have that phi of x will be greater than or equal to 0. Okay, so phi of x naught, that is true, phi of x is greater than or equal to 0 for all x. Hence in particular phi of x naught is also greater than or equal to 0. Okay, now suppose that phi of x naught is strictly greater than 0, then what will happen? Then we'll have that phi of t of x naught, which by definition equal to distance between t of x naught comma t of x naught. Okay, which will be strictly less than distance between x naught comma t of x naught from the condition. Okay, and this, which by definition will be equal to phi of x naught. Hence we got that phi of t of x naught is strictly less than phi of x naught, but this is a contradiction to the minimality of phi of x naught. Okay, hence we'll have that phi of x naught has to be equal to 0. Hence we have distance between x naught comma t of x naught has to be equal to 0. Hence x naught equal to t of x naught. Okay, that means a fixed point exists. Now we also have to prove that it is unique. Okay, so for that take 2 points, both of them let it x and y, let both of them be fixed points. Okay, then we will have that distance between x comma y will be equal to distance between t of x comma t of y, which will be strictly less than distance between x comma y. Okay, why is this happening? Distance between x comma y is equal to distance between t of x comma t of y. This is from the definition of fixed point. Now this is strictly less than distance between x comma y. This is from the a condition that it is satisfying. Okay, but then we are getting distance between x comma y is strictly less than distance between x comma y, which is not possible. Okay, hence the fixed point has to be unique. Now, even in the modified alternative hypothesis, we had said that distance between t of x comma t of y has to be strictly less than distance between x comma y if x is not equal to y, right? Now let's check if we can relax this strict inequality and if we can allow less than or equal to. Okay, so suppose that x is compact and the condition that t satisfies is distance between x t of x comma t of y is less than or equal to distance between x comma y. Now will the conclusions hold or not? The answer is no. Okay, now this is because if we are allowing this equality, we can arrive at two different situations. One is that like it has no fixed point at all. Okay, and other situation is we have a lot of fixed points. Okay, so for example, consider a unit circle S subset of R2. Okay, now this clearly unit circle in R2 is a compact set. Okay, it is closed bounded and it is a compact set. Now consider the map that is rotation by 30 degrees,
anti-clockwise direction. Okay, in that here there is no changing, right? It's just a rotation. So distance between t of x comma t of y will be equal to distance between x comma y, right? Since the circle is just being rotated, the points are, the distance between them won't change. So this hypothesis will be satisfied, but we know in rotation there will be no fixed points, right? Every point will get dislocated, and here there will be no fixed points in such case. Or we might also come into some situations where we have a lot of fixed points. For example, consider an identity mapping from a compact set to itself. In that, every point is a fixed point. Okay, so Banach contraction principle, in that we had a unique fixed point, right? And if we are beginning with some sequence which is defined by in an iterative way as the images, then we are actually converging to that fixed point. But if we are starting with this inequality with less than or equal to, we will not have fixed points and will not have the desired results. So the conclusion is that we can actually have the same results if we are taking a compact set on which distance between t of x comma t of y is strictly less than distance between x comma y. Okay, but it cannot be less than or equal. Okay, so these are the things which I wanted to discuss. So that's all.